In the heart of every atom lies a silent balance between order and collapse. Some nuclei remain stable for billions of years, while others split apart without warning, releasing enormous energy. This phenomenon, known as spontaneous fission, defines the ultimate stability limit of heavy atomic nuclei and sets a hard boundary on how massive an atom can realistically exist. Understanding this limit is not theoretical curiosity, it underpins nuclear energy, nuclear weapons control, and the search for superheavy elements. Spontaneous fission is a radioactive decay process in which a heavy nucleus splits into two or more smaller nuclei without being triggered by an external particle such as a neutron. Unlike induced fission, which is deliberately initiated inside nuclear reactors, spontaneous fission occurs purely due to internal nuclear instability. The heavier the nucleus, the more intense the competition between the attractive nuclear strong force and the repulsive electrostatic force between protons. At some point, repulsion wins. The stability of a nucleus is governed by its binding energy, a measure of how tightly protons and neutrons are held together. In light and medium mass nuclei, the strong nuclear force dominates, keeping the nucleus compact and stable. However, as atomic number increases, the number of positively charged protons grows, dramatically increasing Coulomb repulsion. The strong force is short-range and cannot fully counteract this repulsion across large nuclei. This imbalance pushes heavy nuclei closer to instability. A useful framework for understanding this behavior is the liquid drop model of the nucleus. In this model, the nucleus behaves like a charged droplet of incompressible nuclear fluid. Surface tension, volume energy, and electrostatic repulsion all compete. As nuclei become heavier, surface tension becomes less effective at maintaining shape. When the nucleus deforms beyond a critical point, a fission barrier, an energy barrier preventing splitting, can be overcome through quantum tunneling. When that happens, spontaneous fission occurs. The height of the fission barrier determines how long a nucleus can survive. If the barrier is high, spontaneous fission is rare, and the nucleus may persist for millions or billions of years. If the barrier is low, the nucleus splits quickly. For example, uranium-238 undergoes spontaneous fission very slowly, with a half-life far longer than the age of the universe. In contrast, heavier elements like fermium or californium may fission within seconds or even milliseconds. Neutron-to-proton ratio also plays a critical role. Neutrons act as a stabilizing glue by increasing the strong force without adding electric repulsion. However, adding too many neutrons introduces instability through beta decay. There is a narrow corridor, often called the valley of stability, where nuclei can exist without rapidly decaying. Beyond uranium, staying within this valley becomes increasingly difficult. One of the most fascinating implications of spontaneous fission limits is the concept of the island of stability. Nuclear shell theory predicts that certain superheavy nuclei with magic numbers of protons and neutrons may have relatively higher fission barriers. These nuclei could be significantly more stable than their neighbors, potentially surviving long enough for chemical study. While elements like oganesson have been synthesized, their lifetimes remain extremely short, showing that the island exists, but it is small and difficult to reach. Spontaneous fission also has practical consequences. In nuclear reactors, isotopes with high spontaneous fission rates produce background neutrons that affect reactor control and safety. In nuclear weapons design, spontaneous fission can cause premature detonation if not carefully managed. In astrophysics, spontaneous fission of heavy nuclei contributes to element recycling during neutron-star mergers, influencing cosmic element abundance. Ultimately, stability limits against spontaneous fission define the natural endpoint of the periodic table. They explain why elements do not grow indefinitely heavier and why nature enforces strict constraints on nuclear mass. Every new element synthesized in laboratories pushes against this limit, testing the boundaries of nuclear physics itself. The takeaway is simple but profound: atomic nuclei are not guaranteed permanence. Their existence depends on a delicate balance of forces, and spontaneous fission marks the point where that balance irreversibly breaks. Beyond this line, matter cannot hold itself together, no matter how advanced our technology becomes. If you want to understand where the periodic table truly ends and how nuclear forces decide the fate of matter, subscribe for more deep dive science content and turn on notifications for upcoming videos on nuclear physics, energy, and the limits of nature itself.